Thank you very much to the organizers for giving me the chance to present some of the work that we did over the last decade, I have to say now. And it actually started when I was a postdoc, just a few buildings down towards Dump. And what I would like to talk about today is pattern formation in fluids, in different types of fluids. And I will start with pattern formation in quantum systems and then transition to things that were more motivated originally by looking at bacterial suspensions and other types of active fluids, and what these equations have in common that describe these systems, that they have these higher order derivatives that are there to balance, for example, anti-diffusive terms. And we worked over the last decade on quite a few systems that have these type of equations ranging from buckling and wrinkling problems. So these are where equations that were used to describe experiments performed in pedal rice group, where they were coating soft cores, soft rubber balls with a stiffer film and then basically manipulating them, and you would see these surface patterns. Towards active fluids and also active pneumatics, and what I will talk about today is mostly this part in the bottom left and these in the upper right, which are the fluid-based systems that have vectorial order or polar order. In that case, basically you will have a complex order parameter. But you can extend this idea also to active pneumatics, and we worked a little bit on that. So all these models that I will describe, they are phenomenological in a way. You can think about them basically arising from having a more or larger set of partial differential equations, and you eliminate some equations by some closure conditions to get basically tractable models. So I would like to start with pattern formation in quantum fluids, and this is work that was led by a former postdoc, a recent postdoc, Ville Heinonen, who is now back in Finland. And he was supported by Keaton Burns, who is still in our department, and Keaton is one of the main developers of the Daedalus spectral code, and we use, for most of the simulation that I'll show, basically we use that code, and it's really comfortable also to simulate in complex geometry, so I would really recommend, and they have a very nice gallery, and also these codes for us worked extremely well. Good. So the original motivation was not this one. So the original motivation for us was to think about systems where you can derive in a very straightforward way these higher order contributions to partial differential equations. And what we found at some point is that in quantum system, it's actually quite straightforward to get higher order contributions if you Fourier expand the potentials, and I will demonstrate it. But the experimental motivation comes from basically the recent search, or I mean, probably recent is not the correct word, so for the more long-standing search for supersolids. So supersolids are essentially periodic modulations of quantum gases, quantum liquids, where you still maintain phase coherence. So you do not want the quantum liquid to separate into individual droplets, and I'll show basically examples of that, where that can happen. But what you want is basically just a periodic modulation. And so there were early claims of observations or realization of supersolids in helium-4, but those were later not confirmed, but these experiments or studies still lead to other important insights. More recently, so that is all basically within the last 3 years or so, there were claims basically that there was observation at least of some supersolid signatures in various systems. Yeah, and one idea or one reason why people are interested in those is that you can study fundamental aspects of quantum phase transitions in these systems. So there is a large community studying these with various methods, in particular also quantum Monte Carlo methods, and I will compare our results basically to results from Thomas Pohl's group a little bit later. So they use a very different language from, say, what I'm used to, so the pattern formation language. So what I will present is a slightly different approach, which is complementary and which we think is very straightforward in terms of understanding potential phase diagrams and also patterns that can emerge in these systems. So the basic idea for getting to these anti-diffusive terms in quantum models is fairly straightforward. So many of you probably know the Gauss-Pidevsky or nonlinear Schrödinger equation. So the way you get that equation, for those of you who haven't seen it, is you start from an n-particle Schrödinger equation. You make an assumption about the wave function of all basically particles being in the same wave function. You plug that in, integrate out, and you end up with an effective one-particle equation that looks of this type, so it looks still like a Schrödinger equation, but then there is here a term that can be nonlinear, and where the term comes from is that you have a pair interaction in your n-particle Hamiltonian and you integrate that out. And depending on the assumption that you make about the potential, the pair potential, you get different types of terms here. And if you make the simplest assumption of taking just a repulsive delta potential with some prefactor G0, basically, then you end up with the standard Gauss-Pidevsky equation. So what people have done before, so including basically Wolfgang Ketterle and collaborators, so they have looked at modification of this. So for example, you could replace this by a Gaussian and then basically plug it in here and Fourier expand, and you get a correction which is basically quadratic in that case. But they looked mostly at repulsive term, which essentially enhances diffusion. But you can of course also, assume a general basically expansion of the potential. So here we assume an isotropic potential, so it's expanded in powers of the modulus k, even powers. And if you plug that in, you get a general equation of this type. And now, if you look at the j equals 0 term, then this will give you basically just gp back. And now you can include basically higher derivatives. And what these higher terms essentially encode is the shape of your potential in Fourier space. So you can basically play with these as free parameters, and you can then start looking basically for realizations in terms of actual particle interactions. You could also make these things in principle anisotropic. We didn't do that, so everything I will talk about is isotropic interactions. Good. So this is still a PDE formulated in terms of the complex wave function. You can transform it into more of a hydrodynamic picture by using the standard Madelung transformation. So you start from this equation, and you take your complex wave function and you write it in terms of an amplitude, or the basically square of the density, and a phase. And if you look at the gradient of the phase, that gives you a velocity field, and then it's straightforward to rewrite this equation equivalently in terms of these two fields. And if you truncate here up to fourth order, you get an effective energy that looks like this. And from that point on, you can just analyze basically the pattern that can emerge in this type of system in various ways. And so the relation to anti-diffusion basically is here in terms of the G2 parameter, and the G4 parameter is there to stabilize again. If you want to go to up to that order only, I will show at the end an example where you can in principle go to higher order if you have a way of tuning these interparticle potentials. Good. So here's just one example. So if you add dissipation to your equation, the way you can do that is by just adding basically some damping constant or some non-Hermitian term on the side, and you let the system relax, so you hope to find something that's close to the ground state. So here it's basically in a slightly frustrated state, and if you choose the parameters right, you see you can get these lattices. So this is, in that case, not a super solid, because you can see that the density essentially vanishes in between. So that is a state where you have a lattice of almost independent droplets. What you can do is you can analyze these equations in more detail. So here's an effective interaction parameter, and that spans one axis of the phase diagram. And then there is a second axis, which is given by the average density in your condensate. So it's average number of particles per volume.
It's all two-dimensional?
Everything is two-dimensional here that we do. So also the experimental system are mostly two-dimensional, and we do everything in 2 dimensions. Yeah. But in principle, I mean, there's nothing that would prevent you from doing it in 3 dimensions, so we only did it in 2 dimensions.
But in 2 dimensions, you have Mermin-Wagner's theorem, which says that you cannot have a long-range order in this case if you your interaction is local.
Yeah, but this is, I mean, 0 temperature, so.
So it's only quantum fluctuation, I mean, what?
Yeah, I mean, but here basically they are counteracted by the potential.
Okay.
So yeah, so you have these two parameters, and what you can do is you can use basically different approximations. So the most straightforward thing is to use a one-mode approximation, where you look. So here's basically the potential just rewritten and rescaled. It's the same as before. It's up to fourth order, and you have a dominant wavelength here, which is a Swift-Hornberg type of pattern formation wavelength. And so you choose basically a trial function of this type, and then you can analyze the stability, and you can compute this type of phase diagram where you have a uniform phase, basically up here. You have a single droplet phase if the density becomes very low. You can get a normal solid phase, or that's corresponds to no, I'm not sure that I have an example here, but you have basically a super solid phase. And I will show basically in a second how that differs from the normal solid phase. And you can also get striped phases and so on. So these are all basically mean field predictions based on these one-mode approximations. So the transition basically from super solid to normal solid, for example, can be defined here as the line where the one-mode approximation becomes invalid. Here's a cross-section which compares basically a super solid state, which is shown here in orange, with a normal solid. So for normal solid, we see that the density basically drops to 0 in between, so that results eventually in phase decoherence. And for a super solid, you have these modulations. Now, this is a mean field theory, so you don't know a priori how good it is. So what is useful is to compare against quantum Monte Carlo simulation. So what I did here is I took the same phase diagram, I just flipped it so that I can align it with the way in which it was presented. Basically, the corresponding phase diagram was presented by Thomas Bohl's group in the paper. And so you see they get additional fine structure, but fundamentally, basically, or qualitatively, so there is quite some similarity. And we get it basically in a very straightforward way. So by just doing some pattern formation analysis, these simulations, so they're quite involved. But they also give you more accurate predictions. But to get a qualitative understanding, so these models are quite nice. Now, what you can do is you can, of course, play with the number of terms that you want to include in your potential. So basically play with the shape of your potential. And if you go to higher order, and it doesn't come as a surprise, I think for those of you who are familiar with Swift-Hornberg type pattern formation theories, and you choose basically the parameters in the correct way, you can, for example, create patterns of this type if you want to. So here you have two basically competing wavelengths, and if you tune them in the right way, you get these quasi-crystalline patterns. So an interesting question now is, of course, whether that can be realized experimentally. I think it's further down the road, but for us, I think this is a very nice way of where we can, in a pretty straightforward way, arrive at these higher order terms, and we can study them analytically. And I think if you look at the quantum fluids literature, so very often these type of systems are analyzed in Fock space or in some more or less intuitive way. And I think this pattern formation perspective can potentially contribute something in that area. Okay, so this is what I wanted to present in the first part. And now I want to move forward to models that were inspired.
Yeah. Quick one.
Yeah.
What is the order parameter from the normal solid to supersonic transition?
So here, I mean, so there are different ways of tuning it. So you can tune it using the average density in your system, or you can tune it using the effective attraction in your.
But the two systems have basically the same symmetry. They peak in the same places.
Yeah.
Okay.
Yeah. I mean, as you tune, so the wavelengths may change a little bit. So if you look at here, so we have normalized by the nearest neighbor distance, because these the wavelengths or the typical pattern scale will also be slightly different as you change these parameters. Yeah, but essentially it's like a breakup, so of the modulated phase into individual droplets. So now I want to switch gears a little bit and talk about active fluids, or at least models that were inspired by active fluid experiments. But what you can see here is an Abrikosov lattice, and that Abrikosov lattice will show up as an exact solution basically of these models actually as well. And I'll basically explain how we get there. So another way of looking at it, and it's basically very similar to what we've basically seen in the previous talk, is so we study flows that are driven by some intrinsic linear instability. So no external forcing in anything I show, but everything comes from some sort of intrinsic linear instability. So that work was led primarily by my former PhD student, Jonas Slomka, who is now at ETH and doing entirely different things. So he's looking at horizontal gene transfer in microbial fluids. And Rohit Supekar, who is also a former PhD student, who extended Jonas' work to curved surfaces, and more recently also Nico Romeo, another PhD student who just graduated, continued studying more topological properties of these active flows. And on the numerical side, we were supported by Keaton Burns, Alex Townsend, and Oscar Mikelang was a rotation student who also contributed to one of these papers. Good. So this is where really my interest in these pattern formation models started. It was an experiment performed by Knut Drescher in Ray Goldstein's lab. So just, we see 50 meters that direction. And what you can see here is experimental data from an experiment with Bacillus subtilis. Bacillus subtilis is a 5-micron long bacterium, so it has a propeller. That propeller makes it swim, and if you take many of these bacteria and put them at very high concentrations and confine them in a microfluidic chamber, then they spontaneously form these type of flow patterns. So in this experiment, so the height of the microfluidic chamber was about 100 microns, so it is basically much larger than the size of an individual bacterium. And the other two dimensions were essentially infinite, so they were on the millimeter scale. So it's kind of between 2D and 3D in terms of an experiment. So one thing that becomes quite obvious when you look at these vorticity fields snapshot, that there seems to be some sort of scale selected, a particular vortex size. If you look at, for example, the velocity correlation function at equal time, so you see that it goes negative and has a minimum. So there's roughly a typical vortex size of 70 microns for these experimental settings. So you can tune that vortex size a little bit if you change the chamber height and play with other parameters. But also other groups have found similar results also earlier than actually in these experiments. So these experiments were also done to test some of the theoretical ideas, but this phenomenon was also observed by other groups, including the group of Igor Arnzen, who has done important work there, and even earlier John Kessel. So now, when you look at these type of flow patterns, so the first paper that I know, basically, where basically I could find pattern of this type, also coming from basically some modification of viscosity, as a paper by Dan Rothman, where he looks at Lattice-Boltzmann type gases. And so this is one snapshot from his paper, so that was published in 1989. And you could claim that this is probably the first ever simulation of a bacterial turbulence systems, but it happened way before basically John Kessler's early work with, I think, the first experimental observation was published in 1997. And of course, then basically wasn't thinking about these systems at all, but these ideas are applicable. So what he did is basically he changed the collision rule so that he effectively gets a negative viscosity. So there's another interesting remark, basically. So he says basically once you put this type Fusson and Poisson flow, you get a decrease by viscosity by more than a factor of 2. And this seems also reminiscent of recent reports for bacterial suspensions, where it is claimed that if you have collective dynamics in these systems, you effectively reduce viscosity. So he then got this basically just from playing with the Lattice-Boltzmann type thing, but some of the key features were already in these in his early works. Good. So on the experimental side, just to confirm that there's really an intrinsic scale, and you can actually, use that scale to a certain extent. Ray's former PhD student Hugo Violand was thinking about the possibility of stabilizing vortices. So in these bulk suspensions, they have a lifetime of a second or so. And so what he did is he took a bacterial suspension and mixed it with oil and then you get many of droplets of this type, and he took that mixture and put it between two glass slides. And if you get then a whole ensemble of different droplet sizes, and then if you have droplets that have a diameter that matches approximately these 70 microns, then you get very stable vortices. And so here's an example where the vortex lifetime now becomes of the order of minutes. And if you look at droplets that are too large, the vortex will break up into 2 or more vortices. So the sense of direction here is set by the initial conditions. So you define for 50% of the experiments, you see the vortex going one way, 50% going the other way. So there's some sort of spontaneous mirror symmetry breaking going on in these systems. So the theory basically was for these type of systems was also developed by Francis Woodhouse, who is another PhD student in Ray's lab. And what we did a little bit later is, or I should say what Hugo did, is he now combined many droplets and basically made it possible to have interactions between those. So what you can see is, again, the microfluidic device. So these gray parts are obstacles. These chambers are now here of the order of 50 microns, which is still in that range. And then the droplet, the little chambers can communicate through these gaps. And what I've colored here is the sense of the rotation by computing an effective, basically, angular velocity. And what you find is that if the gap is quite narrow, these droplets spontaneously organize into an antiferromagnetic pattern, which is probably what you intuitively expect. So if the one goes this way, then the other one would want to go this way to minimize basically friction along the boundary. So the interesting thing, and I will not say too much about this, is if you make the droplet size, the gap size larger, then you can tune the system to a ferromagnetic state. And so what happens here is that you get effectively circulations around basically these pillars, and then again it looks like a ferromagnetic antiferromagnetic lattice, just that part of the lattice or the opposite circulations are now localized around you.
So it's the same picture, it's just that you're colouring the thing on the right, is that right?
It's always the same, yeah. So left and right is always the same.
Why do they keep flashing?
Because they are fluctuations. So we compute from these basically data, from the PIV data, we compute basically an angular velocity or an effective angular momentum. And it's just a fluctuating quantity. And sometimes you see also that these spins flip, but then they come back afterward. But so what I'm showing here is just that if you match basically the typical scale, you basically can with some internal confinement you can control these vortices, you can stabilize them. So I just want to make the point here that there is really something like an intrinsic scale selection, because this is now something that we just put into our model using a Swift-Thornberg type term. We take it as a starting point and then study just what the equations give us. Basically. Good. Yeah. So when we looked at first at the bulk experiments, so without confinement and so on, so we were wondering what a simple model might be that we could use to characterize our data. So we tried various things. So there's a long history of active fluid models, so that have many fields. So you can have models that have a density field, that have a fluid, actually a solvent field, can have a velocity field for the active component that you have, that can have a Q-tensor field. So for us, it was very hard to get the phenomenology to work in these models. So we took a step back and came up with basically a phenomenological approach where we said, let's take the TONA2 model, which is the standard model of active motion. I will walk you through the terms, and let's just add a linear instability. So let's put in basically a certain scale selection by hand using a Swift-Thornberg type approach. So the model up to here, basically without the last term and with a positive gamma naught, would be a TONA2 model, incompressible TONA2 model. You have effectively an advective term, so the prefactor here does not have to be 1 if you close to a boundary and then basically solvent, and you have a non-equilibrium system, or you can also motivate it by thinking about the closure of a nematic tensor, so that gives you a modification of this prefactor. You also get a contribution to pressure, which is not as important because you can just use it to redefine pressure. We assume in the model that the velocity field, or whatever our vector field is in that case, is quasi-incompressible. So there are two ways of thinking about the V field here. So one is you think about the mean orientation of the bacteria that you can see, and if you multiply it by some characteristic velocity, you get something like an effective velocity field. So it's a bit of a crude approximation because you have also a co-advection through the fluid and so on, but so that's the simplification that we make. So then there is a polar alignment term or a self-propulsion term that wants to drive you to a characteristic speed in that case. So if the alpha is negative, so alpha over beta gives you a characteristic kinetic energy, that preferred speed. And in the end, basically, we add these two vortex generating term by allowing for this gamma naught to be negative, and that's the relation basically to the topic of that workshop. Okay. Yeah, so as I mentioned, so that's a Tona 2 model married to a Swift-Hohenberg type approach. So what you can do is basically fit these models quite easily, at least roughly, to experimental data. So here's an example. So in these experiments, so what we actually see is a slice through the 3D chamber, usually taken at the middle of the microfluidic chip. But so there is a bit of an averaging going on because the microscope does not really focus in on a single plane. So there's some contributions basically from below and above the plane. In our 2D simulations, we can take a 2D slice. So these simulations were performed by my collaborator Sebastian Heidenreich. And so you get basically very similar qualitative features in these flows. Now, we missed something when we did these first simulations, because we run them on a time scale. We were able to perform these experiments. And Michael Wilczek's group basically was more careful, and they let these simulations basically run for a very long time. And they observed something very, very interesting. So when you, and so there's a reason also why. So in our experiments, so the time on which you can run these experiments was limited because you have a closed microfluidic chamber. Eventually, the system will be depleted of oxygen and the bacteria just stop moving. So we didn't look at these very long times. So what Michael Wilczek did is he took the same equation, just run them for a very long time, and then he observed a very interesting transition. So initially, or for a very long time, you have this turbulent state, but in these models, that state is transient. So after a very long time, the system will eventually settle into a vortex lattice of this type, and you can basically trace it through basically the simulation. They also, so they first published the main idea in a Physical Review Fluids paper in 2018. And what is the key point here is that the pattern scale that you observe, and that's very similar to what we heard in the previous talk, is not the one that corresponds to the most unstable mode, but is actually the one that corresponds to the inner ring of the dispersion relation. Because if you, in 2D, so you can imagine, so you pump in energy at the most unstable mode, and that will dominate for some time, but eventually you have in 2D basically an inverse transport to larger length scales, and that leads you basically to the inner boundary of your stability of your pumping range in K space, so that sets a certain vortex size, and there the dynamics becomes very slow. And this is what you see predominantly in these simulations. So they also pushed it then much further, and they were asking, so what happens basically in very large systems, and you have these type of interesting structures where you have domains that can form and so on. Now, the question is anything like that seen in experiments? And yeah?
So this vortex lattice, is that ferromagnetic or antiferromagnetic?
So that would be so if you only look at these vortices, so that would be ferromagnetic, but because the model is incompressible, so you have counter-rotating stuff in between. But the dominant part is basically that you get these vortices, but then you have to accommodate for mass conservation in the system.
Yeah. On the right picture, you have both signs, right?
Exactly. I mean, so the sign is spontaneously chosen. So there's not. So in this simulation, there's nothing that would explicitly break the symmetry. If you go to an experiment, which I'll show on the next slide, you probably break the symmetry, because if you look at bacteria swimming close to one surface, they will preferentially turn in one direction because their flagella basically have a certain rotation sense. Okay? But in these simulations, so it's totally unbiased, so you just by initial condition you select basically one state or the other, or you have coexistence if your system is large enough.
Just a quick follow-up question. Was it initialized with domains?
No. So it's basically just randomly. So these take very long time. Yeah, so when we submitted the paper, basically, so I was on the second paper, so there was actually a referee and was asking, so why we would waste the energy, that's used to power a village on these simulations, because there is not an experiment. Now, that was a few years ago. So last 2 weeks ago, so there was a paper published in Nature by the Wu Lab, they're based in Hong Kong. And what they report in that paper is a bacterial system which can run for a longer time, and which after some time forms these type of vortex lattices. So I'm not saying that this is exactly what's described in the model, but it's definitely better than them not finding something like that for the model. So what happens in that case is, so in their experiments, they always get the same type of rotation, because the bacteria have an intrinsic, so there is probably an extra term that you would have to add to the model. They actually do that in the paper also, where they add basically one extra term that selects basically one sense of rotation. Yeah. But at least, so it seems that these models, although they are very phenomenological, so they capture some of the things that you see occasionally in experiments. Good. So what we did, and that's actually then was Jonas' PhD thesis, we started wondering, so what would happen if instead of thinking about an effective order parameter field for the bacterial orientation, you would think more about the structures that arise in a fluid? And what would happen if you take Navier-Stokes and you just tweak it in a way that you create a linear instability? And that's very similar to what Moritz basically also, our previous speaker, have been studying. And basically, what could we do with such a model? And so the way we modify the model is really just taking, the Navier-Stokes equation is taking the standard Navier-Stokes and adding higher order terms. So now what we do not have in this model anymore are these potential Toner 2 type terms. So we have to choose a dispersion relation that makes sure that the equations are stable, at least in some regime, and don't blow up, basically. So we need some sort of friction mechanism at large wavelengths and at small wavelengths, and we achieve that by fixing gamma naught and gamma 4 in such a way that we get a suitable dispersion relation, and we tune basically gamma 2, which tells us something about the strength. So the way we think about these models now, it's almost like a closure model, basically on a scale that's much larger than those of the individual organisms. And one nice thing that I will discuss for the next few minutes is that these models also permit exact analytical solutions, and these solutions are to a certain extent also seen in simulations, although they only appear basically as intermittent solutions for certain times, and then the system switches to another stationary solution and so on. Or quasi-stationary solution. Good. So the parameter basically we care about is gamma 2. If gamma 2 is positive, we get basically just pure damping, so nothing interesting happens. If we tune gamma 2 basically in the right range, we get a dispersion relation that looks like this, and this is our active band, basically where we drive. So you can in principle use other type of dispersion relations in Fourier space. They pretty much give you similar qualitative behavior. So these type of models, once we look through the literature, were not, we were not definitely not the first to write them down. So there's early work by Berezhnev and Nikolaevsky who looked at seismic waves. So they have a 1D version of that model. And then there's other work by Tribelski and Suboy who also looked at similar models in the context of soft mode turbulence. I'm sure there are also many other. So what we were interested in is really just looking at the two-dimensional, three-dimensional versions of those models and understanding what they do, and maybe learning something about active fluids, or just in general about systems or flow systems that are driven by linear instabilities. So for the remainder of the talk, I will group these parameters in slightly different ways so that they are more directly interpretable. So you can define basically a characteristic length scale, which corresponds to the most unstable mode. Although I will later show that, again, the patterns that we see are actually the ones usually that are more in this range. So then there's a characteristic time scale that you can associate with these modes, what tau is, and then there is a width of this band of where you pump. And so those are the three parameters I'll be talking about. And that's, again, it's useful for fitting to experimental data if you want to. So you can go to the experimental data that I showed before and can just fit these scales, and effectively you only have to match one. So the tau and the lambda you get directly from the data, and then you can fiddle with the kappa a little bit to get the patterns to match. Good. So let's look at the 2D case first. So you can think of that basically happening in a thin soap film, and there are experiments basically done in such a setting. So you can now take these equations and just apply the usual tools for Navier-Stokes equations. So you can rewrite the equations in terms of the vorticity and the stream function right here. And what you find is basically that you can choose the stream function in such a way that the advective term vanishes, and then to get a stationary solution, you only have to pick your wave number in such a way that the dispersion relation becomes 0. So that means you pick a wave number that's either on this inner or this outer ring. So, and now you can combine in principle modes basically from these rings, and one of the modes, or one of the possible solutions that you can construct are these Abrikosov-type lattices. So by construction, these models, or these stationary solutions, so they are stress-free because we pick the modes so that the right-hand side vanishes in that case. And so you can think of them basically as superfluid in some way, because basically the activity cancels basically the intrinsic viscosity. And so this is reminiscent of what's seen in experiments where at sufficiently high concentrations, so you see a drop in the effective shear viscosity, for example, in these suspensions. But that's more cancellation basically of term that happens. And there's energy input necessary that comes from the bacteria. Good. So you can do the same analysis and find exact solutions on a sphere. And these are also essentially lattices, so you can express them in spherical harmonics and vector spherical harmonics. And so what you want you to focus on here is just, so it's again, it's a 2D flow just on the surface, that you see that the system slows down for a moment in something that looks a bit like a lattice solution, then it transitions to a new lattice solution, and it transitions to a new lattice solution. So the steady state dynamics is almost as if the system is jumping between or in the vicinity of these slow solutions, basically, that you find at these scales. You can make basically the sphere rotating, as we've seen also in the previous talk, by adding an extra term. So what this means is that you actually now only select a subset of the stationary solution, and these correspond to spherical harmonics that just have this stripy structure. And you can then run also the simulations for that. So it's again done in Daedalus. And what you can see here is that you get also stripe patterns. Of course, the length scale is put in through the dispersion relation here. And near the poles, you get these vortex structures that survive, and you also can get Rossby waves. And the nice thing about this type of toy models is that you can do a lot analytically, because you have these steady state solutions, you can expand around them, and so you can do some analysis, and you can basically study a lot of things almost at a textbook type level. Yeah. And then if you want to overreach, you can claim basically that these show some of the features that you see on these pictures that you find on some web pages. Right. But so they're very, so the way I would think about it, so what you can learn from these models is that you really have a very minimalistic model that has only two key ingredients, so one, or actually three. So one is incompressibility, one is a nonlinear advection, and then there's a linear stability that selects a pattern scale. And then you can do quite a bit analytically to study these things. Good. The same approach basically lifts to 3 dimensions. So you can again look for stress-free exact solutions. So the way it works in that case is that you expand your solutions into eigenfunction of the curl operator, so you get a helical basis, and you fix again solutions that make the dispersion relation vanish. But these solutions now come in pairs, and they have a given chirality. And if you look at these solutions in more detail, so because you want to kill the advective term also, you end up with Beltrami fields. So the exact stationary solution that you get in those cases, so I would again stress, so they're not stable, or they're marginally stable because they sit on the boundaries of the dispersion relation. So they are left-handed or right-handed Beltrami fields of well-defined wave number. So the question then again is, once you do a bulk simulation of the full nonlinear system, can you see actually these remnants of these exact solutions somewhere? And this is a solution now already at very long time. So tau was this intrinsic time scale basically. So here we have the order of 100. The 3D simulations done in a periodic domain. And what I would like you to focus on is here basically the helicity and the axis. So green would be 0, blue would be negative, red would be positive, and yellowish. So we don't see any blue in this domain. So the system has spontaneously chosen a state of preferred, basically helicity. And if you analyze the flow fields, so you can check basically how close they are to Beltrami fields. So you find that they are pretty much peaked basically around basically a Beltrami structure. Here we have different the parameters that are varied here are these injection width, and the narrower you make your injection bands, the closer you get to Beltrami. And if you run a lot of these simulations, you will find that with 50% probability, they either go to one basically handedness or the other handedness in these, and it depends on the initial fluctuations. And you can do a triad analysis, and you want to do that to understand why that happens. So very recently, and that's basically discussed here, so we also showed that the same effect happens when you look into confined domains. So we did the same simulation now in a ball without periodic boundary condition. You see all these effects, so they're pretty robust. And the advantage of looking at these closed domains or topologically simply connected domains is that you can now compare to results by Arnold and so on, and compute helicities and leaking numbers in a consistent way and see basically how well these concepts translate. Good. Now, as a last thing, so why is it interesting that we are potentially interesting that we get this autonomous or spontaneous projection onto one helicity subspace? So there has been work by Luca B. Ferrara and collaborators and, on the Navier-Stokes equation. So where they showed is that if you take Navier-Stokes and you project basically artificially in some way onto a subspace of certain helicity, you can get inverse basically transport in that case. So now what these equations do that I just presented, so they spontaneously project onto these subspaces, so you can hope to maybe see signatures of inverse transport also in 3D. And this is indeed what happens when you run these analyze the simulations that I just showed. So here's one case that shows, first of all, that the energy is mostly localized in modes of a certain helicity. It also has a peak, basically at a characteristic wavelength. And if you look at the energy flux, so you find that the modes basically that carry the helicity give you also a partial contribution that leads to an inverse energy cascade. Cascade is too strong. I should say transport. So it's not a cascade. Okay, so let me summarize. So I've presented two models that were on a certain level phenomenological, but in the quantum case you can motivate it just by Fourier expanding microscopic potentials. So both of these models are analytically tractable. On the quantum case, you can get at the one mode level analytic approximations to the phase diagram and predictions basically for where supersolid or quasi-crystalline patterns should emerge. What is an open problem that we haven't looked into, but this could be quite interesting, is the extension to anisotropic potential, and that's because the particles that you use in experiments typically have some polarity. So if you want to make closer connections with these experiments, you would want to look into these type of generalizations. On the generalized Navier-Stokes type active fluid model side, you also get exact solutions. These include basically low stress or zero effective viscosity vortex lattices in 2D, and 3D you have Beltrami flows. And a generic feature of all these models in 2D and 3D is that you select handedness. And What I didn't talk about is you can do more analysis because they are very close, actually much better behaved than the Navier-Stokes equation because you select scales, so you don't have to deal with the power law spectrum. And you can do triad analysis, you can analyze the flow topology. And there's also an interesting relation to Gaussian random fields in that case. And one way to think about these type of models is also that they provide you a random field generator. So if you look at snapshot at sufficiently large time, so you get something that's very close to Gaussian random fields.
Okay.
Questions?
In one of the earlier models, when you were talking about bacterial turbulence, you invented something which is not Galilean invariant.
Yeah.
So that's perfectly okay?
That's okay. So that's a standard thing for these Toner 2 models. So if you have something that lives in the vicinity of a substrate,
Aha,
so
okay.
there's
Okay.
so they're living in a tank, and the tank lives in an environment. So one reason for looking at the Generalized Navier-Stokes model is that we wanted to see what happens if we take a model that is Galilean invariant. So, yeah.
Morris?
Jorn, can you go back to the slide where you had the vortices or the pure vortex forming in a droplet? The experimental work. Yes, this one.
Yeah.
There's this flow around the boundary that goes in the opposite direction of the vortex. Do you know what this is?
Yeah. So that's a very good question, a very sharp observation. So I didn't, and that's actually important for the system, but I didn't want to go into the details. But so what happens in these experiments is, so if you start, say, at lower densities, you will see that bacteria have a tendency to then get stuck near the walls. So the droplets will fill up from the outside to the inside if you go at lower intensity. So now what happens is the bacteria pushing at the outside of the droplet, their flagella will point inward. So they create actually a flow inwards. So the guys that you see swimming on the inside, they actually also point outwards. They're just not fast enough to overcome the flow that's created from the boundary layer. So these systems are quite complicated if you really want to model them accurately. So you really have to be careful about the boundary conditions. They can self-organize their boundary conditions that then go back into the bulk flow.
Tim?
Yeah, this is essentially the same question as I probably asked you when you were working along there some years ago. Your generalized Navier-Stokes equation clearly generates interesting structures which agree rather well with some experiments. The addition of the biharmonic term, in this case the gamma 2 term, is and in this case
Yeah, it's also basically
anyway,
what you're trying to
is a sort of, as you said, phenomenological, but the fact that I've not heard development of that term from microscopic.
So we have
and
yeah.
The fact that that model gives you lots of interesting things doesn't make it physics.
Yeah, so that's a valid point. If we didn't have a microscopic derivation, but we have work published on that, and I think also Morris basically has a separate paper, so there are different ways of getting these terms. So the short is that if you start from a more general set of equations where you have a cube tensor coupling to these equations, if you go in your hierarchy one order further and you close the Q tensor equation, then you can self-consistently add the Q tensor, basically expressed in terms of the flow field. You plug that back in and you get higher order terms. So that's very similar in the same way you would get higher order equations from reaction diffusion systems if you slave one of these equations. That can be done. So when you do that, you get a prediction for these parameters in terms of microscopic parameters, alignment parameters, and so on. The vortex scales that these predict, they are within a factor of 2 what you see in experiments. So in principle, you can do it. What I generally don't like about any of these derivations is that whenever you do these closures, you make ad hoc assumption. So I can give you the answer, we can derive it, because we know also, what we want to get in the end, and it seems to be consistent. But the assumptions that you make along the way, they are, as in these usual closures, pretty coarse. But that's okay. But what I would also say, Navier-Stokes is also an approximation. It's a very well accepted, it's a very good approximation, but it is an approximation.
And it's a derivation. And the nature of that approximation from Boltzmann's equation, for example, is reasonably well.
You have to also do some magic there. So, for example, the advective term in the Navier-Stokes equation comes from a closure of the second moment tensor, where you do a mean field approximation. And as long as that is valid, and it's a good approximation, because otherwise it wouldn't work, so Navier-Stokes works, but you can also get extra corrections, basically, to these equations. So the way I think about these equations is also, if you, say, think about when people want to simulate, say, surface flows or ocean flows, so they look for closures to simulate equations on a coarser scale. So it means that they effectively start to modify Navier-Stokes equation because they project out certain scales. The same happens here. So these equations are not valid on scales of an individual bacterium. But as you coarse grain to these larger scales, you have to effectively account for these terms, and basically that happens. So yeah, that's my answer. So you can derive them from a microscopic model where you take, start from a Langevin equation with hydrodynamic interactions, Stokes interactions between particles, and you go through the procedure. Yeah, I can send you the paper, and I believe, I mean, more also you had also a paper under which assumption you can get these type of models. So there are at least two orthogonal directions where you can get these models, but to me, I mean, at some level, I think that's satisfactory. But also, I know that the prediction for the parameters that I get from these models, they are maybe correct up to a sign, but otherwise, I mean, yeah, it's a sign.
Yeah. That exactly is the follow-up I wanted to ask. When you do these closures, is the sign of gamma 2 something you can choose as you wish?
Yeah, no, the signs come out correctly, so that's what I want to say. So the signs come out correctly, but the magnitude doesn't come out correctly.
Okay, but the sign is more important.
Yeah, it depends. I mean, if you get the sign right, but you're a factor of 10 off in the vortex size, I mean, it's also, but I think with all these, when people do derivations of active matter model from microscopic models, so if you really look at the details, so one thing that you find, for example, that they typically assume that all the microscopic parameters of the underlying microscopic models are the same for all the particles in the system. So basically all the microscopic parameters are drawn from a delta distribution. And that's fundamentally not correct. So if I look at the bacterial suspension, so there will be variability in the swimming velocities, in the size of the bacteria and so on. And all these microscopic derivations, they do not account for that, because once you start to assume sufficiently broad distributions, your closure does not go through in the usual way. So, and that's why, for example, when you do these coarse-grained approximations, so I gave a talk yesterday basically about the learning approaches, you can do the closures, you get a really nice equation, but then you start to simulate that equation, it becomes unstable, for example, at long times. And so if your microscopic model has basically a distribution of parameters. And so I'm a bit, yeah, I like the idea of going from microscopic to macroscopic models, and we have done that. But having done that, also I don't trust the accuracy of these closures for active systems very much, because
Okay, so I think we have this tight schedule for lunch, right? Okay, so let's thank you.